In this class, you're going to learn how to evaluate a definite integral. So a definite integral is one in which the integral sign has got numbers called the limits on the bottom and the top. So when we evaluate one of these definite integrals, we get a numerical solution, so a number, rather than another function. If we've got an indefinite integral, one which does not have the limit, so just the integral of some function f of x, when we integrate that, when we evaluate that, what we get is another function. We don't get a numerical answer, we get some other function and the constant of integration which we stick on the end. So when we upgrade that and we take the integral between, say, a and b of f of x dx, instead of getting some function as our solution, we're going to get some real number, okay, just some numerical value and no constant of integration. So it's another big difference between indefinite and definite integrals. Indefinite integrals have got the constant, which is the nightmare for all integration calculus students because we forget it all the time, and the definite integrals at least don't have the constant on the end. It's just going to evaluate to some real number. So we're going to take a look at these different style of examples in a moment, but before we get to that, let's have a think about the theory. So if we're taking the integral between a and b, so we usually use in generic form a and b as our limits. In reality, they're going to be numerical values, and notice that they go bottom to top, small to large. So the smaller number always goes on the bottom of the integral, the larger number on the top. They can be positive numbers, a mix of positive and negative, or both negatives. That's all fine as long as the smaller number goes on the bottom of the integral sign. So in general terms, the integral between a and b of f of x dx. How are we going to evaluate this? Well, we just take the integral as normal. So using our normal rule, the power rule, the chain rule, trig rules, whatever rule you need to use to get the integral. But that integral, remember, is actually an antiderivative, okay? That's what an integral is. It's the opposite of a derivative. Usually when we're talking about a function f, we notate its antiderivative using uppercase f. So when we evaluate this definite integral, the answer we're going to get is the indefinite integral, or the antiderivative, and we're then going to evaluate that at the upper limit, so f of b minus f of a. So this is essentially your formula, if you like, called the Fundamental Theorem of Calculus, a really important result in calculus. This is your formula for evaluating these definite integrals, but it maybe makes it more complicated than it actually is. It's basically just taking the integral and then subbing in the numbers, putting the top number, the upper limit in first, and subtracting from that the lower limit. Pretty easy process really once you've got it down and once you've worked a few examples. The challenge is not so much learning the formula, it's being able to apply it to different scenarios. For example, here we've got a trig function. This I think is not meant to be a 2, I think this should be a pi, or in fact let's make it a pi by 6, something like that. So yeah, we've got a trig function here, we've got a non-integratable form here, and then we've got a couple of more standard polynomials. So it's learning to adapt to the different scenarios that's going to be more challenging. So let's just jump into these examples. So how do we integrate? Well, we can use the power rule here. So if you integrate 2x, remember that's 2x to the power of 1, increase the power by 1, that goes up to a 2, divide by the new power, you would end up with 2x squared over 2. That will simplify to just x squared. So this just becomes x squared, 4 integrates to 4x. If we were doing an indefinite integral, that would be us done, apart from putting the plus c on the end. But with definite integrals, we place these inside a square bracket and we move the limits over to the right hand side, okay? So that's just part of the process that you need to get used to, just subbing in the numbers like that. Keep the order, so the lower and the upper stay as the lower and the upper over there. But this inside part is just your normal integration rule to get from there down to there. What we then do is sub in the upper limit. So this is now evaluating the f of b part. This basically is our f part, our uppercase f. This is our antiderivative. We're going to sub in the 3. So usually it's good practice to use a bracket for this. So we're going to put a 3 in here. So 3 squared plus 4 times 3. So that's like our f of b part. We're going to subtract from that our f of a part. So it's going to be 1 squared, which is just 1, plus 4 times 1, which is just 4. So 1 plus 4 is 5. Try not to put in like too many lines of working. You don't need, I mean, there's no point in writing in 1 squared plus 4 times 1, because that's just going to waste a line of work in, it's going to waste time. Just go straight to putting a 5 in there. Just do it in your head, basically. If they get more complicated, then take more lines of work in, but for a trivial number like that, just leave it like that. So checking this guy out, we've got 3 squared, which is 9. We've got 4 times 3 is 12. 9 plus 12 is 21. And then we're going to take away 5 from that. So the final answer there would be 16. So notice we did get what we expected. In other words, a real number solution. Okay, so pretty easy, right? That's all we do. We just integrate as normal and then learn how to stick the numbers into the integral to get our final numerical answer. Let's look at this guy, fairly similar. We've got a negative limit to deal with. That doesn't really change things. So the integral is going to go in a square bracket. The integral of 5 is 5x. When we integrate x cubed, we're going to get x to the power of 4 over 4. So just using the power rule there, increasing the power by 1, dividing by the new power. So at this point, again, we've taken our integral, just like we would with an indefinite integral. Now we're just going to evaluate it at these limits. So sticking in the numbers, basically. So 5, remember, we're putting in the upper limit first. So 5 times 1 is 5 minus 1 over 4. So that's just going to be 5 minus 1/4. Taken away from that, this is really important to use brackets for these, mainly because of the minus. It means that you can then control things like double negatives, which are quite common in these questions. So minus 2 times 5 is minus 10. Minus 2 to the power of 4 is going to go to a positive number because the power is even. You can work out carefully yourself if you wish. I mean, it's minus 2 times minus 2 times minus 2 times minus 2, which ends up being 16, positive 16. Positive 16 divided by 4 is 4. There's a minus here, so it's going to be minus 4. So integration is great for working on your numeracy and fractions. So just check my work in there. I did it fairly quickly. So how do we take this forward? Well, a little bit tricky because we've got a fraction in here, but you would basically just simplify it. So you could turn the 5 into 20 over 4. So it's going to be 20 over 4 minus 1 over 4. Here we've got minus 10 minus 4 is minus 14, but then there's a minus outside, so that's going to go back to a plus 14. And then you just keep simplifying this until you get some numerical answer. So for example, that becomes 19 over 4. Shall I carry on with it? Yeah, let's carry on. So this is going to become 19 over 4. We would need to combine that with this number by making this into something over 4. To achieve that, just times 14 by 4, which is 56. And then you're going to get a final answer. It's a bit of an ugly looking number, but the final answer is going to be 75 over 4, if my counting is correct. So maybe just check my numbers there. It's quite common to get fractions and to get weird looking numbers for your answers here. And that's primarily because when we're integrating using the power rule, we're dividing by the new power. When you're dividing, you're quite often introducing a fraction like we did here. It was that fraction here that's basically resulted in the fractional final answer. So that's pretty common. Your fractions have got to be quite sharp in integration because these are generally going to be non-calculator questions. Not always, sometimes they're calculator, but you should be able to evaluate these, assume you're going to have to evaluate these non-calculator. Okay, right, let's take a look at this guy. So slightly different scenario here because this is in a non-integratable form. Two issues we've got to deal with. So the square root is non-integratable, the fraction is non-integratable. We can change the square root into a 1/2 power. A half power is integratable, but it's still on the bottom of the fraction, so we'll need to bring that up to the top. So it's going to end up being the integral between 1 and 4 of 2x to the minus 1/2 dx. So integration is also really good for pushing on your indices rules so that you can get really sharp with those. You'll see a lot of things that are in a non-integratable form, just like differentiation. Non-integratable form, non-differentiable form, got to generally use indices rules to get it into a integratable or differentiable form. So we're good to go now with this thing here. It's a little ugly because it's got a fraction in it. So we're going to use the power rule. Increasing the power by 1 is going to go up to a power of 1/2. We're then going to be dividing by that 1/2, but dividing by 1/2 is the same as multiplying by 2. Remember, if you're dividing by a fraction, you just flip the fraction and multiply by it. So this power here, this is all going to go in a square bracket. This power here is going to go up to a 1/2 because we're increasing the power by 1. Minus 1/2 plus 1 is 1/2. positive 1/2. We're dividing by 1/2, but that's the same as timesing by 2. Timesing by 2 will combine with this 2 to end up actually being a 4 in there. So you might need a couple of lines of working in there yourself just to make sure that that is correct. Check my working, make sure you understand what I did there, but you're going to see a lot of these where you're dividing by a fraction because you're dividing by the new power. Just flip that fraction and times by it because that's how we evaluate dividing by a fraction. Okay, so what does this give us? Well, we're going to get 4 times, I'll maybe write this one out. So we're going to get 4 times 4 to the half, but the half power is the same as the square root. So we're going to get 4 times the square root of 4 minus 4 times the square root of 1. I'm just going to put my answer up here. Square root of 4 is obviously 2 times 4 is 8. So we get 8 in our first bracket. Square root of 1 is 1 times 4 is 4. So it's 8 minus 4, giving us a final answer there of 4. So different to these two polynomial type functions, this one was in a different form, a non-polynomial. We had to use a couple of indices rules to get it into an integratable form. Once we got it into the integratable form, like this guy here, everything else was just the same. Just maybe bearing in mind though, when you're working with fractional powers, to evaluate those, when you put the numbers in, you're going to have to turn them back into some kind of root. So starting to get a little bit more complicated, a little bit more going on there, and like I say, really pushing your indices rules a little more. Okay, let's think about this one. First of all, it is in an integratable form for a trig function. When you integrate cosine, that integrates to positive sine, the opposite sign to when you differentiate. Remember, when you differentiate cosine, it goes to negative sine. Confusingly, in integration, it goes to positive sine. So we are going to evaluate this as 2. The 2 stays there basically, so 2 sine x, and just pulling our limits over. So even though it's a trig function, we don't change the technique. We take the antiderivative, we take the integral basically of 2 cos x, which gives us 2 sine x, put that inside our square brackets, move the limits over. At that point, we're done with the integration part, and we just need to work on evaluating the numbers basically. So going back to our kind of formula, f of b minus f of a, f of b is going to be 2 sine pi by 6, and then we're subtracting from that f of a, which is 2 sine 0. So to be able to evaluate this, you need to use trig exact values. If it was a calculator question, which most students will be hoping for, you can just fire it in the calculator. Here though, we need to probably work these out manually. It's in radians as well, which is, makes it a little trickier, I guess, but pi by 6 is the same as 30 degrees. And the sine of 30 degrees is 1/2. So this is basically going to be 2 times 1/2. The sine of 0 is 0. So maybe just think about that from the sine graph. So when you're at 0 along the way, on the x-axis, you're at 0 up the way on the y-axis. So the sine of 0 is 0, so we just get a 0 there. So 2 times 1/2 obviously is 1, minus 0 is 1. So that evaluates to a final answer of 1. So that's just 4 quick examples of different types of scenarios. So you've got 2 polynomial type functions, a trig function, and a non-integratable form. These are probably the ones you're going to see most of. You will see a lot of these as well. You're going to use these once you get this thing into the integratable form. It's going to look a little bit like a polynomial, although it might have a negative power or something, or fractional power up here. But this technique of getting it from a non-integratable form into the integratable form is quite often how you'll be starting these questions. So unfortunately, you need to get really good with your indices rules. In addition to that, the main takeaways are obviously knowing the kind of main formula here. This is key to being able to solve these. Having the expectation that the answer is going to come out to be some real number rather than some function. And then it's just learning the technique and being really careful where you're working, making sure to use these brackets to separate things out to avoid making numerical mistakes. Integration is a great topic for practicing your indices rules, your fractions, your numeracy, just a whole bunch of things. It's quite painful at the time, but if you're a calculus student, if you're studying differentiation or integration or calculus in general, this is definitely something to spend a bit of time on. It's painful, but you'll find that at the end of it, your skills are a lot sharper. So I hope that makes sense. Any questions, just fire them in the comments below, and I'll get back to you soon.